Hello. So the final two types of problems that we are going to use dimensional analysis to solve are problems where we're converting rates, like a meters per second to a kilometers per hour, and what is on problems 29 and 40, where we are converting cubic and squared units. We know that, let's say, 100 centimeters equals 1 meter. But if I think about 100 square centimeters, the area that a square, 100 centimeters on one side and 100 centimeters on the other side, does not equal 1 meter. So for instance, I can't just say 100 centimeters squared equals 1 meter squared. What is that area? Well, it'll be 100 times 100, or 100 squared. Basically, what we need to do is anytime we're converting units that are cubic or squared, we just need to square or cube everything inside the conversion factor. If I look at question 39, it says convert 26.4 square centimeters to square meters. So this would be an area type problem. Always circle the do and underline the clue. And of course, I'm going to write 26.4 square centimeters out front. Now, I could memorize all the different conversion factors for all the squared units, how many square nanometers there are in a squared kilometer. It would be so many more units and conversion factors to memorize. What we can just do is use those 5 conversion factors that we know and then manipulate them. I can take any conversion factor. So I'll rewrite this. We learned the conversion factor that 100 centimeters equals 1 meter. How do I turn that into the conversion factor for squared units? It's very simple. You literally just square everything in it. And really, the only number that you need to worry about is the number that's not 1. So this is the conversion factor that I'm going to put in my parentheses. 100 squared centimeters squared is equal to 1 squared meter squared. Now we know that when you square the number 1, it just equals 1. And so what am I plugging into my calculator here? I'm plugging in 26.4 divided by, because the 100 is in the bottom, and I would need to do 100, either the caret and the 2 or just 100 squared. I want to make sure that I don't forget to actually plug this part into my calculator. That's the most common mistake that students make with that. When I do that, look what happens. The units that I don't want cancel out, and I am left with 0.00264 meters squared. Right, the unit that's left is the unit of my answer. This number has 3 significant figures, so my answer has 3 significant figures. Those first 2 zeros are not significant. Let's do the next problem, problem number 40, in the same way. How many cubic centimeters is 0.3990 cubic meters? So again, what is the real conversion factor that I'm using, or what is the most basic conversion factor that I'm using? 1 meter is equal to 100 centimeters, and then I go ahead, and because this is a cubic problem, I cube everything, not just the units, but also the numbers. That's a big deal, the numbers in the conversion factor. So now when I go to do this problem, 0.3990 cubic meters. Circle the do, underline the clue, set up my parenthesis. 1 cubed meter cubed is equal to 100 cubed centimeters cubed. This is what I plug into my calculator now. I plug in 0.3990 times 100 cubed. Again, not scientific notation, just 100 cubed. When I do that, my answer is 399,000. centimeters cubed. And at the end of these problems, I always want to make sure that my units cancel out. So the cubic meters cancel out. The only unit that is left is centimeters cubed. And then I look at significant figures. This number here has 4. The number as I wrote it, 399000, has how many? 3. That's right. So this is a problem. What can I do? Well, I know that if I put a decimal point after those, that can make those zeros significant, but now that has 6. Neither one of these are right. I needed to have 4. When you have a situation where you can't really get the right number of significant figures, the easiest way to rectify that is to put that number into scientific notation. Because by definition, a number in scientific notation will always have a decimal point. Decimal point is going to make those zeros significant. So think about, we're going to make the number 3.990. That has 4 significant figures. Times 10, and then how many times would I have to move my decimal point? 1, 2, 3, 4, 5. So 3.990 times 10 to the positive 5 centimeters cubed is my answer there. And that's how I can get the same number of significant figures that I started with, 4. And the last type of problem that we will use dimensional analysis to convert are problems where we're converting the entire unit, and the entire unit is a ratio. So we are converting, let's say in problem number 41, the density of gasoline, we're converting it from grams per milliliter to kilograms per liter. What we do, or the key to this, is similar to what we did before, is just rewriting that slash sign. This time I just want to rewrite it so that it looks more like the fraction that it is. So when I rewrite this, I'm going to rewrite 0.680 grams in the numerator and milliliters in the denominator. And I'm going to write it more like a fraction so that when I convert those units, I know what needs to go where in my conversion factor to cancel them out. So the first thing, and what I usually wind up doing, is converting the top unit first, grams to kilograms. I know that 1,000 grams equals 1 kilogram. So 1,000 grams goes in the denominator, 1 kilogram goes in the numerator. That's going to make it so that those units of grams cancels out. I need to do this again now to convert milliliters to liters. 1,000 milliliters equals 1 liter. Where is the 1,000 milliliters go? On the top. Why is that? In order for the units to cancel out. So it's really important that we write our given information as a fraction with a very distinct numerator and denominator. Now this is something that is very interesting. It only works every once in a while, where I would take that 0.680, I would then, first thing would be to divide by 1,000, then I would multiply by 1,000. You don't even need a calculator. The answer is just going to wind up being the exact same thing, 0.680. What units haven't canceled out? Well, a kilogram in the numerator and a liter in the denominator. And that's what my answer needed to be. Right? Then when I circled the do, that's what it said. Here's the last one that we're going to do together. Again, you can always pause this. Try this one on your own. Light travels at 2.998 times 10 to the positive 8 meters per second. What is the speed of light in kilometers per hour? So I take the number that's given to me, 2.998 times 10 to the positive 8. This is the most important part, making sure that you write the meters in the numerator and the seconds in the denominator. The abbreviation for seconds can be a number of different abbreviations. It can be S or SEC, and either one of those is fine. I would just suggest that if you are going to use a singular S, that you do put it in cursive. An uncursive S looks very similar to most people's 5, and you just want to make sure that that's not confusing. So I'll always put it in cursive. So meters per second, and now I'm going to make my conversions. The first thing I'm going to convert is meters to kilometers, and writing the conversion factor over here, 1,000 meters is 1 kilometer. So I'm going to put 1,000 meters on the bottom and 1 kilometer on the top so that the units of meters will cancel out. The next thing that I need to do is convert from seconds to hours. If you don't know how many seconds there are in an hour, you can break this into 2 different parentheses. So I'm going to show you a few different ways. There are, in fact, 3,600 seconds in 1 hour. So I can do 3600 on the top, 1 hour on the bottom. And then in my calculator, 2.998 second comma to get an E8, then divided by 1,000, then multiplied by 3,600. I get to 4 significant figures, 1.079 times 10 to the positive 9 kilometers per hour. Right, how do I get those units? Meters cancel, seconds cancel. So kilometers in the numerator, hours in the denominator. If you did not know that there were 3,600 seconds in an hour, you could do this a little bit differently. So I would do the same thing, 2.998 times 10 to the positive 8 meters per second, the same first parenthesis, 1 kilometer in the numerator and 1,000 meters in the denominator. And you may not know that there's 3,600 seconds in an hour, but you know, there's 60 seconds in a minute. So you could do 60 seconds on the top and 1 minute on the bottom. And then you do just one more parenthesis with 60 minutes on the top and 1 hour on the bottom. If you do it that way, do you see that the units still cancel out? Your meters cancel, seconds cancel, minutes cancel, so you would be left with a kilometer on the top and an hour on the bottom. And it comes out to be exactly the same answer. 4 significant figures in the stem of my scientific notation, and again, 4 significant figures in my stem there. The last question is sort of a challenge question to encompass a whole bunch of different strategies that we have learned over the past few videos. It says Earth is approximately 1.5 times 10 to the positive 8 kilometers from the sun. How many minutes does it take for light to travel from the sun to the Earth? Light travels at 2.998 to the times 10 to the positive 8 meters per second. There's many different ways to try this problem. I want you to get creative, try as many different ways as you can think of, and we'll talk about the answer to this and how you approached it the next time we're all together.